Okay, continuing on with class 24, here's another example. We're going to continue with the pump that we used in the 2 videos ago to find the power via the geometry and speed using the velocity triangles. And now this is a pump curve for that pump. And still have a 7.5 inch diameter impeller. And with these traits, this pump curve. So you can see here's the 7.5 inch diameter impeller on that curve, and we use it with 140 degree Fahrenheit water. So we look up the properties and find the vapor pressure, and here's the specific weight. The flow rate is 320 gallons per minute. And the pump inlet is 10 feet above the open surface. And the head loss on the pump inlet side, we've already done that, is 8 feet. So we don't need to calculate that, but we could from our minor and major losses. And the suction is a 6-inch ID, and the discharge is a 4-inch ID. And the height between the inlet and the outlet is negligible. So first we want to find out what the pump head is going to be. So based on this curve right here, we take that 320, oops, let me just go back up to here, 320, and we see where it intersects right about there. Right, so doing our best, little comparison over there. I estimate that to be about 210 feet. You should recall, or you could recall, you look back over the other video, I believed in the ideal case, what we ended up with was 311, is that right? No, 303, right? So we had 303, but this is going to be the HP, so I'll write it out, it's HP actual. 210 feet, where HI was 303 according to our velocity triangles, 303.1 feet. So interesting. Let's go ahead and take a ratio. 210 divided by 303.1 is 69.28%. So that would be a first type of efficiency that we might want to find. What is the hydraulic power added to the water according to what we have here? Well, we'll take this and we'll take the hydraulic power. And so that's going to be, recall, gamma HP actual time volumetric flow rate. So 61.38, and HP was 210. We already did that 320 gallons per minute into cubic feet per second. I already did that conversion, so I'm going to write it down anyway. 0.713. I'll divide by 550 here to get it into horsepower. And we get 16.71 horsepower. You'll recall that previously we got 24.17. In the next part, we want to find the efficiency according to the pump curve. And so looking at this carefully, it appears we're between 68 and 70 right here. So let's say that it's an efficiency of approximately 69%, which agrees with what we had anticipated from our previous example. We also ask, what is the required motor horsepower based on these two things, right? But from B and C. So we're going power required, I guess. And what I'll do is I'll say we'll take our omega hydraulic, not omega, the W dot hydraulic, and divide it by efficiency. And what we end up, we get 24.22 HP. Where recall I had 24.17, so really, really close. And not to mention, right here, we were relying on being able to read the graph. So it's our pencil width, or pen width, I guess, in this case. So does this agree with the pump curve? Now, we have to, this is a difficult one because of the way they have these labeled right here. Right? Here's 30 horsepower, and here's 20 horsepower. And there's 15 horsepower. But if you look at this, right, so if let me change colors here so you can see that this curve, right, okay, that this is not following this curve that's right next to it. It's actually following this line right here. And this, you can see there's a line right here as well. And then there's a line right here. So these are the lines of power. That sounds kind of evil, the lines of power. These are lines of power. And you can see that this one must be this curve. So this one must be this curve. And this one must be this curve up here. So this guy right here is actually 25 horsepower. And you can see that we landed right on it. I know, it's weird how they labeled it. I mean, you can see like right here, they've labeled this guy, he is 10 horsepower. But for whatever reason, they didn't bother to label this. And here right here is 40 horsepower. So working backwards, that has to be, this line right here has to be 25 horsepower. So yes is the answer to that. What is the available net positive suction head? Right, so that requires actually doing somewhat calculation for F. So the net positive suction head available is going to be, first take atmospheric 14.7, multiply it by 144, divide it by the specific weight, 61.38. And you need to have seen the previous video here where we figured out what that was going to be right here. So that's what we're doing. So there's the atmospheric pressure, and then we subtract out lift. Right. So we're going to subtract out. It's got to raise it 10 feet. Right. The pump is located 10 feet above the open surface. And then we need have a head loss of 8 feet. So subtract out the head loss. And then lastly, subtract out the vapor pressure, which we've looked up already as 2.888. And that's because it's a higher temperature, that it has a higher vapor pressure. Multiply it by 144 to get it in pounds per square foot. And then divide it by 61.38 to get it in terms of head. And we find that we have 9.711 feet. All right, so that's the answer to F. And it says, what is the required net positive suction head based on the pump? That's going to be, let's see, we'll switch over to another color here, blue. And so right there. And if we look very carefully, I think I can say pretty safely that it's right around there or there. So I'm going to call that 8 feet. So we require 8 feet, and we have 9.7 available. So would you expect this to be a problem? Say no. No cavitation problem. But close, right? It's close. And we might want to have a better margin than that, because the next question is, what about after 10 years? And I would say my opinion, said, would you? It says, would you have it? I would say yes, likely, because things degrade, and including the impeller, the housing, the pipes can get rougher, so you can increase the head losses. There can be a lot of different things, and this margin isn't enough between 9.711 feet and the 8 feet, right? And then the last part of the question, what do you expect the suction pressure gauge to read? I guess I got a little carried away with the Bernoulli here. But it is something that we would want to consider, that you'd want to find a pressure right here and a pressure right here, because there's usually pressure gauges on each side of the pump, and you would have some anticipated things that you'd want to see right here. So we would have on the suction side of the thing, we would label this 0.1, and maybe I'd label that 0.2, and maybe I'd label that 0.3. So for the, let's switch to green. I like green. So for what would you expect the pressure gauge to read right there? What I would simply do was to take P2, I'll do it in terms of head, plus V2 squared 2G. Now this would be an actual of velocity, so you wouldn't set that one equal to 0. Here's the pressure, what you want the pressure gauge to read. So you'd find this velocity due to the 6-inch inlet at that volumetric flow rate, and then you would have the Z2, and this would be the 10 feet, right? Because that would be where this was located, and we'll set this as the datum. And then you would say that was equal to, well, we could have P1 divided by gamma, and this is going to be atmospheric right there, just notably. V1, that's going to be 0 because it's going to be at that free surface. Z1 is going to be at the datum. And then we would have the head losses that we just encountered, right? And then we'd be able to solve for P2. So the P2, in this case, it ends up being a 6.940 psi-A. So it's good that we could stick an atmospheric pressure there, then we won't get a negative pressure onto the thing. Which, by the way, most gauges will read it in inches of mercury vacuum. So we would find, this would be the gauge right here, and here would be 0, but the needle would be in that direction, right in there. So here would be absolute 0. This would be measuring from that direction, but we would turn it around and measure it from that direction right there to see how much distance it was away from there. And then the last question, same idea. What do you expect the discharge pressure gauge to read? I would now probably take it from right here instead, or what did I do here? No, I went ahead and took it from right here. All right, that's not too bad. Because it would still have these same losses up to there. Yeah, that would make sense. But now what I would do is I would add in the HP right there, right? So I would go P3 gamma plus V3 squared 2G, right? So we're going to be able to find V3 because we have the volumetric flow rate and that diameter. It's going to be the same height. V2 and V3 are going to be equal to each other. And then we have P1. We could take this as atmosphere or treat it as 0 because we're probably going to use gauge pressure for this. It's going to be a positive pressure, so that makes sense right there. So just go ahead and go 0. V1 is squared 2G, and then this is the datum. Get rid of the head losses, but now we're going to have the HP is what we would be placed into there. So we're going to be able to find what P3 would be equal to, and I get 113.1 PSI G. So we've come full circle, and not full circle, but we've come all the way through and used first principles, not first principles, maybe. Yeah, I guess say. We'd use velocity triangles to find the power output, and then we've used the actual practical pump curves. Wow, there's a lot in this class. Our next video is coming up.